In classical physics, empty space was treated as a passive backdrop. It was a geometric stage on which objects moved and forces acted, but it possessed no properties of its own. In Newtonian mechanics, space existed independently of matter, extending infinitely in all directions, but nothing happened inside it unless a particle or a force was present. If all matter were removed from a region, what remained was a true vacuum, an absence, a container stripped of contents. Even in classical electromagnetism, where fields filled space, the vacuum itself was still regarded as inert. Electric and magnetic fields could exist in empty regions, but the emptiness was merely where those fields happened to be defined. Space itself did nothing. This picture began to fracture in the early 20th century. Relativity replaced the rigid container of classical space with space-time, a structure that could bend, stretch, and respond to energy and momentum. Even so, a vacuum in general relativity initially seemed simple. Remove all matter and radiation, and space-time becomes a smooth solution of Einstein's equations. The vacuum was no longer entirely passive, but it still appeared empty in a meaningful sense. Curvature could exist, gravitational waves could propagate, but there was still an intuition that if all physical content were stripped away, nothing substantial would remain. Quantum theory overturned that intuition at a much deeper level. In quantum mechanics, the idea of a system with exactly zero energy is no longer generally possible. The uncertainty principle enforces a limit on how precisely complementary quantities can be fixed. For particles, this means that confinement implies motion. For fields, it means that the very notion of complete stillness becomes ill-defined. When quantum field theory replaced particles with fields as the fundamental objects of nature, the concept of a vacuum changed from absence to a specific physical state, the lowest energy configuration of those fields. In this framework, every point in space is occupied by quantum fields. These fields are not optional additions layered on top of empty space. They are the basic ingredients of reality. The electron field, the electromagnetic field, the quark fields, and many others permeate all of space-time. What we call particles are localized excitations of these fields, much like waves on the surface of an ocean. Removing all particles does not remove the ocean, it leaves the water in its calmest possible state. That calm state is what physicists call the vacuum. Calling this state nothing is misleading. The vacuum is not defined by what is missing, but by what remains when all fields are in their lowest energy configuration, consistent with quantum laws. Even in that configuration, the fields do not vanish, they fluctuate. These fluctuations are not disturbances added from outside. They are intrinsic to the quantum nature of the fields themselves. The vacuum is therefore restless by necessity, not by accident. This shift from particles to fields is central to understanding why classical intuitions fail. In a particle-based worldview, it makes sense to imagine removing objects one by one until nothing remains. In a field-based worldview, there is no procedure that removes the fields themselves. Fields are not objects sitting in space. They are what space is filled with at a fundamental level. Space without fields is not part of the theory. The vacuum is simply the particular state in which those omnipresent fields have minimal energy. Even the phrase empty space becomes problematic. In everyday language, empty means devoid of content. In physics, vacuum means something much more precise and much less intuitive. It refers to a well-defined quantum state with measurable consequences. The vacuum can exert forces, influence particle behavior, and affect the evolution of the universe. None of this fits the idea of nothingness. The transition from classical vacuum to quantum vacuum also reflects a deeper conceptual change in how reality is described. Classical theories often begin with entities, particles, bodies, objects, and then define the space between them. Modern physics reverses this order. It begins with fields defined everywhere, and objects emerge as particular patterns within those fields. The vacuum is not the absence of objects, it is the baseline condition of the fields themselves. This baseline condition is not arbitrary, it is constrained by the equations governing each field and by quantum principles that prevent complete stillness. Even when a field is in its ground state, its energy does not vanish. The lowest energy state is not zero, but a finite value determined by the field's allowed modes of oscillation. Each mode behaves like a quantum harmonic oscillator, and quantum oscillators retain energy even in their lowest state. This residual energy is an unavoidable feature of the theory. The vacuum, then, is a physical state with structure. That structure is subtle and often invisible, but it is real. It does not resemble matter or radiation, yet it cannot be dismissed as mere mathematical bookkeeping. Experiments have repeatedly shown that altering the conditions of empty space changes observable outcomes. The behavior of atoms, the propagation of light, and the forces between objects can all depend on the properties of the vacuum. It is important to emphasize what the vacuum is not. It is not a sea of particles popping in and out of existence in any literal sense. That image is a heuristic, useful in certain calculations, but easily misunderstood. The vacuum is not a chaotic froth of miniature objects. It is a well-defined quantum state of continuous fields, governed by precise mathematical rules. Its fluctuations are statistical features of field operators, not tiny objects appearing and disappearing in space. Understanding vacuum as a state rather than an absence also clarifies why it can vary. Different physical situations can have different vacuum states. Boundary conditions, background fields, and space-time curvature can all modify what counts as the lowest energy configuration. A vacuum near a massive object is not identical to a vacuum far from it. A vacuum in an expanding universe is not identical to a vacuum in static space-time. There is no single universal emptiness. This flexibility would be impossible if vacuum truly meant nothing. Nothing cannot change, respond, or interact. The quantum vacuum can do all of these. It can store energy, transmit influence, and even determine the large-scale behavior of the cosmos. Treating it as a physical state, rather than a void, is therefore not a philosophical preference, but a necessity imposed by observation and theory. The replacement of particle-only intuition with a field-based view is one of the most profound shifts in modern physics. It removes the comfort of imagining space as an empty container and replaces it with a picture in which space is always filled, always active at a fundamental level. The vacuum is the quietest configuration available to the universe, but quiet does not mean empty. It means balanced, constrained, and defined by laws that leave no room for absolute nothingness. From this perspective, emptiness becomes a misnomer. What we call empty space is better understood as space in its ground state, structured by quantum fields that cannot be switched off. The vacuum is not the absence of reality. It is the foundation upon which all observable phenomena are built. Modern physics is built on a reversal of an older intuition. For centuries, matter was understood as a collection of objects moving through space. Particles were the actors, space was the stage, and fields, when they appeared at all, were auxiliary tools for describing forces between objects. That hierarchy no longer survives contact with experiment. In contemporary physics, the fundamental entities are not particles, but fields, and particles are better understood as temporary, localized expressions of those fields. A quantum field is a physical quantity defined at every point in space-time. It is not a substance poured into space, nor is it something that occupies space in the way matter does. Rather, it is inseparable from the definition of space itself within the theory. Each known type of particle corresponds to its own quantum field. An electron field, a quark field, a photon field, and so on. These fields exist everywhere, regardless of whether any particles are present. This statement often sounds abstract, but it has concrete meaning. Consider the electron. In a particle-based picture, electrons are tiny objects that sometimes exist and sometimes do not, depending on whether they are present in a given region. In a field-based picture, the electron field exists everywhere at all times. What changes is whether that field is excited. When the field is excited in a localized way, an electron is observed. When it is not, the field remains in its ground state, but it does not disappear. This framework resolves several otherwise puzzling facts about nature. One of the most basic is particle identity. All electrons are exactly identical, down to every measurable property. Classical physics offers no deep reason why this should be so. Quantum field theory does. There is only one electron field. Every electron is an excitation of the same underlying entity. There is nothing to distinguish one excitation from another beyond its state of motion and interaction. The sameness of particles is not an assumption but a consequence. The same reasoning applies to photons. A photon is not a small packet of light travelling through emptiness like a bullet. It is a quantized excitation of the electromagnetic field. When no photons are present, the electromagnetic field still exists. It simply resides in its lowest energy configuration. Turning off a light source does not remove the field from space. It removes energy from it. This is why modern physics cannot meaningfully describe a universe without fields. Fields are not optional ingredients added to explain interactions. They are the core of the description. Space without fields is not a physical possibility within the theory. Even imagining such a situation requires stepping outside the framework that successfully explains experimental results. Once fields are treated as fundamental, the concept of empty space must be redefined. Empty space no longer means space with nothing in it. It means space in which all quantum fields are in their ground state. That ground state is what physicists call the vacuum. It is a specific physical condition, not the absence of physical content. The ground state of a quantum field is not trivial. In classical physics, the lowest energy state of a system is one in which motion has stopped completely. A pendulum at rest has zero kinetic energy. A classical wave can be reduced to zero amplitude. In quantum physics, this idealization fails. The uncertainty principle prevents a system from having both a precisely defined value and a precisely defined rate of change. For fields, this translates into an inability to eliminate fluctuations entirely. Each mode of a quantum field behaves mathematically like a harmonic oscillator. These oscillators are not physical springs, but the analogy captures the essential structure. In quantum mechanics, a harmonic oscillator cannot have zero energy. Its lowest possible energy state still contains residual motion. This residual energy is called zero-point energy, and the associated activity is zero-point motion. Zero-point motion is not a defect or a sign of instability. It is a stable, unavoidable feature of quantum systems. Even at absolute zero temperature, when all thermal energy has been removed, zero-point motion remains. Cooling a system reduces excitations above the ground state, but it cannot eliminate the ground state fluctuations themselves. Because quantum fields exist everywhere, zero-point motion exists everywhere as well. There is no special location where fields are absent or inactive. The emptiest intergalactic void contains the same underlying fields as the interior of a star. What differs is the presence or absence of excitations, not the presence of the fields themselves. This is a profound departure from particle-based intuition. In a particle picture, it is natural to imagine removing particles from a region and being left with nothing. In a field picture, removing particles means returning the fields to their lowest energy configuration. Something remains, and that something has physical properties. The vacuum is therefore not inert. It is the baseline state of a complex system of interacting fields. Its properties influence observable phenomena. Atomic energy levels depend on vacuum fluctuations. Forces can arise due to changes in vacuum structure. even the large-scale behavior of the universe is sensitive to the energy associated with vacuum fields. It is important to be precise about what fluctuates in the vacuum. Popular descriptions often invoke images of particles popping in and out of existence. While this language can be heuristically useful, it is not literally accurate. What fluctuates are the values of field operators. These fluctuations are statistical features of the quantum state, not brief appearances of classical objects. Treating them as such leads to confusion. Zero-point motion does not imply chaos or randomness in the everyday sense. The vacuum state is highly constrained and well-defined. Its fluctuations have specific correlations and distributions dictated by the underlying equations of the theory. They are not arbitrary disturbances, but the minimal activity consistent with quantum law. The unavoidable presence of zero-point motion also explains why the vacuum responds to changes in environment. When boundary conditions are altered, the allowed modes of a field change. This modifies the pattern of zero-point fluctuations. The vacuum adjusts accordingly. The response is measurable because the vacuum is a physical state of real fields, not an abstract mathematical artifact. This sensitivity becomes especially important in curved space-time or in expanding universes. The definition of a vacuum state depends on the geometry of space-time itself. What counts as the lowest energy configuration in one situation may not be the same in another. As a result, different observers or different cosmic eras may disagree on what the vacuum is. This is not a paradox, but a reflection of the fact that vacuum is a state, not a universal absence. The field-based view also clarifies why attempts to eliminate vacuum energy entirely fail. In classical thinking, one might imagine subtracting off the energy of empty space as a meaningless reference. In quantum field theory, vacuum energy arises from the same mechanisms that give rise to particle behavior. Removing it by fiat would break the internal consistency of the theory. The challenge is not that vacuum energy exists, but that its consequences are difficult to reconcile with gravity. From this perspective, particles become secondary, emergent features of a deeper structure. They are convenient for describing experiments because detectors respond to discrete excitations. But treating them as fundamental obscures the continuity and omnipresence of the underlying fields. The vacuum is not what remains after particles are gone. It is the default condition of the fields that give rise to particles in the first place. Every point in space contains fields because space itself is defined in terms of those fields. There is no underlying empty container waiting to be filled. The fields are not contents of space. They are part of the framework that defines what space is. Asking for space without fields is like asking for waves without water or vibrations without a medium, except that in this case the medium is fundamental. Zero-point motion ensures that this medium is never perfectly still. Even when the universe is as cold and quiet as it can be, the fields continue to fluctuate in tightly constrained ways. This residual activity is not something that happens in addition to the vacuum. It is the vacuum. Understanding fields before particles is therefore essential for understanding why emptiness is restless. The vacuum is not a blank canvas waiting for reality to be painted onto it. It is already structured, already active, already participating in physical processes. Particles come and go, but the fields remain, defining the conditions under which anything can exist at all. This inversion of perspective, from objects to fields, from emptiness to ground state, marks one of the deepest conceptual shifts in physics. It replaces the idea of a universe built from things with the idea of a universe built from continuous entities whose excitations appear to us as things. In that universe, empty space is not the absence of reality. It is reality in its most restrained, minimal energy form, governed by laws that allow no true stillness anywhere. Zero-point energy arises directly from the structure of quantum mechanics, not from any particular physical system or experimental complication. It is not added by hand, nor does it depend on temperature, environment, or observation. It appears the moment classical variables are replaced by quantum ones. The origin of zero-point fluctuations lies in the way quantum theory constrains what it means for a system to be at rest. In classical physics, stillness is well defined. A particle can have a precise position and zero momentum. A field can have a precisely defined value everywhere and remain static indefinitely. Energy can be reduced continuously until it reaches zero, at which point motion stops. This intuition fails once quantum principles are imposed. The failure is not due to technical limitations or measurement imperfections. It is a structural feature of the theory. Quantum mechanics replaces classical variables with operators that do not generally commute. This non-commutativity imposes limits on how precisely certain pairs of physical quantities can be specified simultaneously. The most familiar example involves position and momentum, but the same structure applies to fields and their conjugate momenta. For a quantum field, the fundamental quantities are the field value at a point and its rate of change. These play roles analogous to position and momentum for a particle. Quantum mechanics enforces an uncertainty relation between them. If the field value is fixed precisely, its rate of change becomes maximally uncertain. If the rate of change is fixed, the field value becomes uncertain. There is no state in which both are exactly zero everywhere. This immediately rules out the classical notion of a perfectly still field. A field configuration with zero value and zero motion at every point would violate the uncertainty principle. The lowest energy state consistent with quantum rules must therefore involve fluctuations. These fluctuations are not optional, they are the minimal activity required to satisfy the structure of the theory. Mathematically, this becomes clear when quantum fields are decomposed into modes. Each mode behaves like an independent harmonic oscillator. This is not an analogy, but an exact correspondence within the formalism. Each allowed wavelength of the field contributes a degree of freedom with its own energy spectrum. In classical physics, a harmonic oscillator can have zero energy. In quantum mechanics, it cannot. The lowest energy state of a quantum harmonic oscillator has a non-zero energy proportional to its natural frequency. This residual energy is the zero-point energy of that mode. Because a quantum field has infinitely many modes, the vacuum contains an enormous number of such contributions. Even when no particles are present, every mode retains its zero-point energy. This result is unavoidable once the field is quantized. It does not depend on the specific type of field or on the details of interactions. Scalar fields, fermionic fields, gauge fields all exhibit zero-point fluctuations, though the mathematical structure differs slightly between them. The presence of residual energy in the ground state is a universal feature. Zero-point energy should not be confused with random noise. The vacuum state is highly ordered. Its fluctuations have precise statistical properties determined by the field equations. Correlations between fluctuations are fixed. The vacuum is not chaotic, it is constrained. The fluctuations do not represent instability or decay. They represent the lowest energy configuration allowed by quantum law. Temperature plays no role in their existence. Lowering the temperature of a system removes thermal excitations, energy associated with particles and collective motion above the ground state. At absolute zero, all such excitations are eliminated. What remains is the ground state itself. Zero-point energy survives unchanged. This distinction is essential. Thermal motion depends on temperature and vanishes as temperature approaches zero. Zero-point motion does not. It is present even in a perfectly isolated system cooled to absolute zero. It cannot be extracted as usable energy, nor can it be removed by cooling. It is not energy stored in the usual thermodynamic sense. It is a baseline offset imposed by quantum structure. The persistence of energy at absolute zero is not a paradox. It does not violate thermodynamics, because zero-point energy cannot be converted into work without changing the system's boundary conditions. It is not a reservoir that can be tapped. It is part of the definition of the ground state itself. For fields, this means that the vacuum is never truly inactive. Even in the absence of particles, the field values fluctuate around their mean. These fluctuations have measurable effects. They modify the behavior of atoms, shift energy levels, and influence the propagation of radiation. These effects are small but real, and they disappear if zero-point fluctuations are artificially removed from the theory. It is sometimes tempting to treat zero-point energy as an artifact of calculation, something to be subtracted away as an unphysical infinity. This approach works in certain contexts, particularly when only energy differences matter. However, the fluctuations themselves cannot be eliminated without destroying the predictive power of the theory. They are responsible for observable phenomena that have been confirmed experimentally. The idea that fields cannot be perfectly still also clarifies why vacuum is a state rather than a void. A void would imply absence of activity. The quantum vacuum is active by necessity. It represents the minimal, irreducible level of activity compatible with quantum constraints. Anything quieter would violate the uncertainty principle. This also explains why vacuum properties depend on context. Because zero-point energy arises from field modes, anything that alters the allowed modes alters the vacuum. Boundaries, curvature, and background fields change the spectrum of fluctuations. The vacuum adapts because it is defined by the collective behavior of these modes, not by an abstract absence of content. From a conceptual standpoint, zero-point energy marks the precise boundary between classical and quantum thinking. In classical physics, zero energy means nothing happens. In quantum physics, zero energy is not a permissible state for most systems. The ground state still contains structure, correlations, and measurable influence. The existence of zero-point energy is therefore not an exotic prediction. It is the most conservative outcome of applying quantum principles consistently. It follows directly from the uncertainty principle extended to fields. If quantum mechanics is correct, zero-point energy must exist. This realization reshapes the meaning of emptiness. Even when all particles are removed, even when temperature is reduced to absolute zero, even when no radiation is present, the fields that define reality continue to fluctuate. The universe cannot be perfectly quiet. The vacuum is not a static backdrop, but a dynamic baseline, restless in the only way quantum law allows. Zero-point energy is the simplest expression of that restlessness. It is the energy that remains when nothing else can be taken away. The phrase virtual particles occupies an unusual place in modern physics. It appears frequently in popular explanations, is used casually even by professionals, and yet it is one of the most commonly misunderstood concepts associated with the quantum vacuum. To understand vacuum fluctuations properly, it is necessary to separate what virtual particles actually represent from what they are often imagined to be. In quantum field theory, physical processes are calculated using perturbative methods. Interactions between fields are expressed as expansions, with each term representing a possible way the interaction could occur. These terms are conveniently visualized using diagrams, now universally known as Feynman diagrams. In these diagrams, lines represent propagators of fields, and vertices represent interactions. Some lines begin and end at external points, corresponding to particles that enter or leave an experiment. Other lines begin and end only within the diagram itself. These internal lines are what physicists refer to as virtual particles. A virtual particle is not a particle in the same sense as an electron detected in a laboratory or a photon measured by a sensor. It is not an object traveling through space, and it is not something that can be directly observed. It is a mathematical contribution to an interaction amplitude. The internal lines of a Feynman diagram represent how fields propagate between interaction points within a calculation, not physical trajectories of particles appearing in space and time. This distinction is crucial. Real particles are associated with well-defined energy and momentum relationships. They satisfy what are called on-shell conditions. Their energy and momentum obey precise equations determined by their mass and the speed of light. Virtual particles do not satisfy these conditions. Their energy and momentum are not constrained in the same way. They exist off-shell, meaning they are not physical states that could be isolated or measured. The common image of virtual particles popping in and out of existence arises from a misinterpretation of this formalism. It is tempting to imagine a vacuum filled with tiny particles spontaneously appearing, borrowing energy for a brief moment, and then disappearing again. While this picture is often used as a teaching aid, it is not an accurate description of what the mathematics is doing. Nothing is literally appearing in space, travelling for a short time, and then vanishing. Vacuum fluctuations are better understood as fluctuations in field values, not as transient particles. The vacuum state of a quantum field has non-zero variance. The field does not sit at a fixed value everywhere. Instead, its value fluctuates around a mean. These fluctuations are encoded in correlation functions, which describe how the field behaves at different points in spacetime. Virtual particles emerge when these correlations are expressed using particle-based language, but the underlying reality is field-based. The idea of temporary excitations is also often misunderstood. In quantum field theory, an excitation that corresponds to a real particle is one that can propagate freely and be detected. It carries energy and momentum that can be measured independently of the interaction that created it. A virtual contribution, by contrast, exists only as part of a larger process. It cannot be separated from that process. There is no moment at which a virtual particle exists on its own. This is why statements about virtual particles violating energy conservation are misleading. Energy conservation is never violated in quantum field theory. What happens instead is that intermediate states in a calculation are not constrained to satisfy the same relations as observable states. The total process always respects conservation laws. The intermediate mathematical objects are not physical states evolving in time. Vacuum fluctuations appear naturally when calculating observable quantities. For example, consider the interaction between charged particles. Even in empty space, the electromagnetic field fluctuates. These fluctuations modify the effective interaction between charges. When these effects are calculated, they appear as loops in Feynman diagrams. These loops involve virtual contributions of the electromagnetic field and charged fields interacting with themselves. The result is a measurable correction to forces and energy levels. In atomic physics, vacuum fluctuations shift the energy levels of electrons in atoms. These shifts are small but measurable. They arise because the electron interacts not only with external fields, but also with the fluctuating electromagnetic field of the vacuum. In calculations, this interaction is represented by virtual photons exchanged between the electron and the vacuum. Again, the photons are not physical objects flying around the atom. They are terms in the calculation that encode how the field fluctuates. Experimental confirmation of vacuum fluctuations does not involve detecting virtual particles directly. Instead, it involves observing the effects of fluctuations on measurable quantities. When predictions that include vacuum fluctuations match experimental results, it confirms the underlying field theory. The success of these predictions does not require interpreting virtual particles as real entities. The particle metaphor has limits, and those limits become especially clear in the context of the vacuum. Particles are useful for describing how detectors respond. Detectors register discrete events, so it is natural to describe interactions in terms of particles entering and leaving. Inside the calculation, however, the language of particles becomes less reliable. Fields and their correlations provide a more accurate description. This is why different mathematical formulations of quantum field theory can lead to the same physical predictions without ever invoking particles explicitly. Path integral methods, operator methods, and algebraic approaches all describe vacuum fluctuations without requiring the notion of particles popping in and out of existence. Virtual particles are a bookkeeping device, not a fundamental component of reality. The distinction between real and virtual becomes even clearer when considering stability. Real particles persist unless they decay through specific interactions. Virtual contributions do not persist at all. They have no lifetime, no trajectory, and no independent existence. They are simply parts of a mathematical expression that contribute to a probability amplitude. Another source of confusion arises from the way time is treated in calculations. In perturbative expansions, interactions are integrated over all possible times. This can give the impression that intermediate states exist for short durations. In reality, the calculation does not describe a sequence of events unfolding in time. It describes the net contribution of all allowed processes consistent with the theory. The notion of a virtual particle existing briefly is a narrative imposed on a calculation that does not have such a temporal interpretation. Understanding these limits is essential when discussing the vacuum. The vacuum is not a sea of particles in motion. It is a quantum state of fields with specific statistical properties. Virtual particles appear when that state is described using particle-based language, but they should not be mistaken for physical inhabitants of empty space. This does not make the concept meaningless. On the contrary, virtual particles are indispensable for practical calculations. They allow complex interactions to be decomposed into manageable terms. They encode how fields influence one another, even in the absence of real particles. Their mathematical role is precise and essential. Problems arise only when the metaphor is taken too literally. When virtual particles are imagined as real entities, questions arise that have no physical meaning. Where exactly are they? How long do they exist? How do they avoid detection? These questions stem from applying classical intuition to objects that are not objects at all. The correct interpretation keeps the focus on fields. Vacuum fluctuations are fluctuations of fields. Virtual particles are internal representations of those fluctuations within a particular calculational scheme. Real particles are stable excitations that can propagate and be detected. Confusing these categories leads to conceptual errors. The vacuum, then, is not populated by fleeting objects. It is characterized by non-zero correlations between field values. These correlations influence physical processes in subtle but measurable ways. They alter forces, shift energy levels, and contribute to the structure of interactions. All of this happens without invoking particles appearing from nothing. Recognizing the limits of the particle metaphor does not diminish the strangeness of the vacuum. It clarifies it. The vacuum is not strange because it contains tiny objects doing impossible things. It is strange because the lowest energy state of a quantum field is not static. It fluctuates in a way that has no classical analogue. Virtual particles are one way of talking about that fluctuation, but they are not the fluctuation itself. They are a language choice, useful but limited. The deeper reality is field-based, continuous, and governed by statistical laws that resist visualization. Understanding this distinction is essential for any serious discussion of vacuum energy. Without it, the vacuum becomes a cartoon. With it, the vacuum becomes something more subtle and more interesting. A structured quantum state whose effects are real, measurable, and unavoidable, even though the entities used to describe them in calculations are not themselves physical objects. The Casimir effect provides one of the clearest demonstrations that the quantum vacuum is a physical state with measurable consequences. It shows that changing the structure of empty space changes the behavior of matter, even when no particles are present. Importantly, it does this without appealing to speculative physics. The effect follows directly from standard quantum field theory and has been confirmed experimentally with increasing precision. The basic setup is deceptively simple. Two uncharged, parallel conducting plates are placed very close together in an otherwise empty region of space. Classical physics predicts nothing unusual. With no electric charges, no currents, and no applied fields, the plates should experience no force. Quantum field theory predicts otherwise. The key idea is that the vacuum is not empty, but filled with fluctuating fields. These fluctuations can be described as a superposition of modes, each corresponding to a possible wavelength of the field. In unbounded space, all wavelengths are allowed. When boundaries are introduced, this changes. The conducting plates impose constraints on the electromagnetic field. Only certain modes can exist between the plates, while a larger set of modes remains available outside. This difference matters because each mode contributes zero-point energy. The vacuum energy between the plates is therefore different from the vacuum energy outside them. The system lowers its total energy by reducing the separation between the plates, increasing the imbalance between inside and outside modes. The result is a force pulling the plates together. This force does not arise because the plates are charged or interacting through classical fields. It arises because the allowed structure of the vacuum has been altered. The plates change the boundary conditions of the electromagnetic field and the vacuum responds. The force is a consequence of geometry and quantum fluctuations, not of matter-exchanging particles in the usual sense. It is important to understand what is doing the work here. Nothing is emitted from the vacuum. No particles are produced or absorbed in a detectable way. The force is static and persistent. It reflects a difference in vacuum energy density caused by the presence of boundaries. Once the plates are in place, the force exists continuously. The Casimir effect is often explained using the language of virtual particles pushing on the plates. While this picture can be suggestive, it is not fundamental. The force does not depend on imagining particles bouncing between surfaces. It depends on the modification of field modes. A more accurate description focuses on how the spectrum of vacuum fluctuations changes when boundaries are introduced. The effect is extremely small. For plates separated by a distance on the order of 1 micrometer, the force is measurable but tiny. At larger separations, it becomes negligible. This smallness is not a weakness of the effect, but a reflection of the scale at which quantum vacuum fluctuations become relevant. Despite its subtlety, the Casimir effect has been measured repeatedly. Early experiments confirmed its existence qualitatively. More recent experiments have achieved high precision, accounting for factors such as plate geometry, surface roughness, temperature corrections, and material properties. The measured forces agree with quantum field theory predictions to high accuracy. These experiments matter because they rule out the possibility that the Casimir effect is a mathematical artifact. The force depends on separation distance in a specific way predicted by theory. Altering the geometry or materials alters the force in predictable ways. This consistency across setups confirms that the vacuum responds physically to boundary conditions. At the same time, it is essential to be clear about what the Casimir effect does not demonstrate. It does not prove that vacuum energy can be extracted as usable energy. The force arises from differences in vacuum energy between regions, not from the absolute value of vacuum energy itself. Once the plates reach equilibrium, no further energy can be obtained without changing the configuration. It also does not show that virtual particles are physically real objects. The calculations can be performed entirely in terms of field modes and boundary conditions without invoking particles at all. The particle language is optional and sometimes misleading. The Casimir effect does not resolve the deeper problem of vacuum energy and gravity. The force depends on changes in vacuum energy, not on its absolute magnitude. This distinction is crucial. Quantum field theory predicts enormous vacuum energy densities, while cosmological observations indicate a much smaller effect. The Casimir effect confirms that vacuum energy differences are real, but it does not explain why the absolute value behaves as it does in gravity. There is also no violation of conservation laws. The energy gained when plates move closer comes from the work done by the force as the configuration changes. Restoring the plates to their original position requires input energy. The system behaves consistently with thermodynamics and mechanics. What the Casimir effect ultimately shows is that empty space is sensitive to structure. The vacuum is not a fixed background that remains indifferent to matter. It reacts to boundaries, geometry, and constraints in measurable ways. This reaction is not exotic or speculative. It is a direct consequence of quantizing fields. The effect also illustrates the limits of classical intuition. In classical physics, removing all matter and radiation leaves nothing that can exert a force. In quantum physics, removing particles leaves fields, and fields have ground states with structure. That structure can produce forces when disturbed. In this sense, the Casimir effect is not surprising once the field-based view of reality is accepted. It is simply one of the most accessible manifestations of vacuum structure. Its importance lies less in its magnitude and more in what it reveals conceptually. The vacuum is not an inert void. It is a physical state with measurable properties. The Casimir effect demonstrates this without appealing to extreme energies, cosmological distances, or speculative theories. It operates in tabletop experiments using well-understood physics. At the same time, it sets clear boundaries on interpretation. It does not imply that the vacuum is a reservoir of free energy waiting to be tapped. It does not require imagining particles spontaneously appearing and disappearing. It does not solve the cosmological constant problem. It shows something more precise and more constrained. By altering the allowed modes of a quantum field, boundaries change the vacuum state. The vacuum responds with a force. That force is real, measurable, and exactly what quantum field theory predicts. Nothing more is needed, and nothing less will do. In this way, the Casimir effect serves as a quiet but decisive reminder that empty space, in modern physics, is neither empty nor passive. It is structured, responsive, and governed by laws that give even nothing a measurable presence. Quantum electrodynamics, or QED, is the most precise physical theory ever constructed. Its predictions agree with experiments to more than 10 decimal places. At the same time, it contains some of the most severe conceptual difficulties in all of physics. Vacuum energy sits at the center of this tension. It is unavoidable in the theory, mathematically enormous and yet largely invisible in most laboratory phenomena. Understanding how QED handles vacuum energy requires confronting infinities directly, not avoiding them. In QED, the electromagnetic field and charged matter fields are quantized. Once this is done, every mode of every field contributes 0-point energy. For the electromagnetic field alone, each allowed mode behaves like a quantum harmonic oscillator, and each oscillator contributes a fixed minimum amount of energy even in its lowest state. The number of modes is infinite. As a result, the total vacuum energy obtained by summing over all modes diverges. It is not merely large, it is infinite. This divergence appears immediately when the theory is written down. It is not a subtle higher-order correction. It is present before any interactions are considered. Even the free electromagnetic field, without electrons or charges, has an infinite vacuum energy density according to naive calculation. At first glance, this looks like a catastrophic failure. A theory that predicts infinite energy density for empty space would seem to be physically meaningless. Yet QED is extraordinarily successful. The resolution lies in understanding what kinds of quantities are physically meaningful and how the theory is organized to make predictions. The key point is that QED does not directly predict absolute energies. It predicts energy differences and observable effects. In most non-gravitational experiments, only changes in energy matter. Shifting all energies by a constant has no observable effect on particle dynamics, atomic spectra, or scattering processes, as long as gravity is not involved. This allows physicists to redefine the zero of energy. In practice, the infinite vacuum energy is subtracted away. This procedure is part of a broader framework known as renormalization. Renormalization is not a trick to hide infinities. It is a systematic method for relating the parameters appearing in the mathematical formulation of a theory to the quantities that are actually measured. In QED, the quantities that appear in the equations, bare masses, bare charges, and bare energies, are not directly observable. What experiments measure are effective masses, effective charges, and energy differences that already include the influence of vacuum fluctuations. Renormalization re-expresses the theory in terms of these physical quantities. Vacuum energy enters this process in a specific way. The infinite contribution from zero-point fluctuations is treated as part of the definition of the energy reference level. Since only differences in energy affect observable electromagnetic processes, this subtraction does not alter any measurable prediction within QED itself. This is not an ad hoc choice, it is enforced by consistency. If the vacuum energy were not subtracted, every calculation would be dominated by an infinite constant that cancels out when differences are taken. Renormalization formalizes this cancellation and ensures that finite, testable results remain. The same logic applies to other infinities in QED. The interaction of an electron with its own electromagnetic field produces divergent corrections to its mass and charge. These divergences are absorbed into redefinitions of the electron's physical mass and charge. Once this is done, the theory makes finite predictions that match experiments with extraordinary accuracy. This success is not accidental. Renormalization works because QED is a renormalizable theory. Its infinities can be absorbed into a finite number of physical parameters. Once those parameters are fixed by experiment, all other predictions follow. Vacuum energy, however, occupies a special position. Unlike mass and charge, it does not correspond to a parameter that can be directly measured within QED alone. Its absolute value does not affect electromagnetic interactions in flat space-time. As a result, QED provides no internal constraint on the magnitude of vacuum energy. It simply allows it to be shifted arbitrarily without consequence as long as gravity is ignored. This freedom is both a strength and a weakness. It allows QED to function as a predictive theory despite infinite vacuum energy. But it also means that QED cannot explain why vacuum energy should take one value rather than another. The theory permits enormous values and offers no mechanism to suppress them. When vacuum energy is estimated using reasonable physical cutoffs, the numbers are staggering. If the zero-point contributions of known fields are summed up to energies associated with known physics, the resulting vacuum energy density exceeds the value inferred from cosmology by many orders of magnitude. If the sum is extended to even higher energies, the discrepancy becomes extreme. This is not a numerical inconvenience, it is a profound conceptual problem. According to QED and related quantum field theories, empty space should possess an enormous energy density. According to observations of the universe, the vacuum energy that influences cosmic expansion is tiny by comparison. Reconciling these two facts is one of the deepest unresolved problems in physics. Within CAD itself, this problem is invisible. Because gravity is not included, vacuum energy can be discarded without consequence. The theory remains internally consistent and empirically accurate. This creates an uncomfortable situation, a theory that works perfectly in its domain but seems fundamentally incomplete when confronted with gravity. Despite this discomfort, CAD's predictive success is unquestionable. Calculations that include vacuum fluctuations reproduce experimental results with extraordinary precision. Effects such as shifts in atomic energy levels and corrections to magnetic moments depend sensitively on vacuum contributions. Removing these contributions would destroy agreement with experiment. This demonstrates an important point. Vacuum fluctuations are not optional features of the theory. They are essential. The same zero-point structure that leads to divergent vacuum energy also produces finite, measurable corrections when differences are considered. One cannot keep the successes while discarding the underlying structure. Physicists therefore accept a pragmatic compromise. Within non-gravitational quantum field theory, vacuum energy is treated as unobservable and is subtracted away. This allows the theory to function and make accurate predictions. The unresolved tension with gravity is acknowledged but deferred to a more complete theory. This approach reflects a broader pattern in theoretical physics. effective theories are constructed to describe phenomena within a certain range of scales. They are not expected to answer every question. KED describes electromagnetic interactions with unmatched accuracy. It does not claim to be a complete description of nature at all scales. From this perspective, the enormity of vacuum energy in QED is not a failure of calculation. It is a signal. It indicates that the theory is being pushed beyond the domain in which its assumptions can be trusted. In particular, treating space-time as a fixed background while assigning it infinite energy density is inconsistent once gravity is taken seriously. The fact that QAD remains predictive despite this inconsistency is remarkable. It suggests that vacuum energy couples very weakly, or in a highly constrained way, to the phenomena KED describes. Understanding why this is the case likely requires new physics, not adjustments within QED itself. Renormalization, then, is not a denial of vacuum energy. It is a way of isolating what can be predicted reliably from what the theory cannot yet explain. It preserves the influence of vacuum fluctuations on observable processes while discarding an absolute offset that QED is not equipped to interpret physically. The conceptual discomfort remains. The theory asks us to accept that empty space contains an enormous amount of energy that does not manifest in most experiments. It also asks us to trust a procedure that subtracts infinities in a controlled but abstract way. These are not minor issues. They reflect the limits of the framework. Yet the alternative, rejecting the theory, would mean discarding one of the most successful achievements in the history of science. Instead, physicists accept QED as an extraordinarily accurate description of electromagnetic phenomena while recognizing that its treatment of vacuum energy is incomplete. Vacuum energy in QED is therefore best understood as both real and unresolved. It is real in the sense that vacuum fluctuations have measurable effects that are confirmed by experiment. It is unresolved in the sense that the theory assigns them an energy density that cannot be reconciled with gravity. This dual status is uncomfortable but informative. It tells us that the vacuum is not a passive backdrop, and it tells us that our current theories describe it only partially. KED handles vacuum energy with mathematical discipline and empirical success, even while leaving its deepest implications unanswered. The vacuum in QED is not empty, not quiet, and not fully understood. It is a structured quantum state whose fluctuations shape the behavior of matter and light, and whose energy content points beyond the theory that describes it so well. In modern physics, energy is not just a bookkeeping quantity. It is a source of gravity. This statement is not optional or interpretive. It is built directly into the structure of general relativity. Any form of energy, momentum, or pressure contributes to the curvature of space-time. There is no special exemption for energy that happens to belong to empty space. In general relativity, gravity is not described as a force acting within space. It is described as the geometry of space-time itself responding to physical content. That response is encoded in Einstein's field equations, which relate space-time curvature to the stress-energy tensor. The stress-energy tensor is the object that summarizes all forms of energy and momentum, mass density, kinetic energy, pressure, stresses, and energy flux. If something carries energy, it appears in this tensor. If it appears in this tensor, it gravitates. This is why vacuum energy immediately creates tension. Vacuum energy is energy. It arises from quantum fields, and it is present everywhere. If general relativity is correct, that energy must curve space-time. There is no mechanism within the theory to selectively ignore it. The stress-energy tensor does not distinguish between familiar forms of energy and unfamiliar ones. Radiation contributes, matter contributes, pressure contributes, even negative pressure contributes. Vacuum energy, if it exists as a real energy density, must appear as a term in the stress-energy tensor. Once it does, space-time must respond. To understand how vacuum energy enters gravity, it helps to look at its mathematical form. A vacuum state is defined by symmetry. It looks the same in every direction and at every point. There is no preferred frame, no flow of energy, no spatial variation. This symmetry severely restricts the form of the stress-energy tensor associated with vacuum energy. The only stress-energy tensor compatible with complete homogeneity and isotropy is one proportional to the space-time metric itself. This corresponds to a constant energy density filling space uniformly, accompanied by a pressure that is negative and equal in magnitude to that energy density. This is not an assumption. It follows directly from symmetry. This form has a crucial consequence. In general relativity, pressure gravitates just as energy density does. Ordinary matter has positive pressure, which enhances gravitational attraction. Vacuum energy has negative pressure. That negative pressure does not cancel gravity. It changes its character. When the stress-energy tensor has this vacuum form, the resulting space-time curvature does not pull matter together. Instead, it causes space itself to expand at an accelerating rate. The effect is not localized, it acts everywhere, uniformly, on the large-scale structure of the universe. This behavior was already present in Einstein's equations before quantum field theory existed. Einstein originally introduced a term called the cosmological constant to allow for static solutions. He later abandoned it, but mathematically, it never went away. A constant energy density filling space is exactly equivalent, within general relativity, to a cosmological constant. Once vacuum energy is recognized as real, this equivalence becomes unavoidable. Vacuum energy behaves gravitationally like a cosmological constant. It should cause the universe's expansion to accelerate. This is where the conflict emerges. Quantum field theory predicts that vacuum energy exists and that its density should be enormous. General relativity predicts that any such energy must strongly influence space-time curvature. If both theories are applied naively and simultaneously, the result is catastrophic. Even a modest vacuum energy density would dominate the dynamics of the universe. If the vacuum energy predicted by quantum field theory were present gravitationally, space-time would curve so violently that galaxies, stars, and even atoms could not exist. The universe would either collapse instantly or expand explosively, depending on the sign of the energy. Yet the universe we observe is neither violently collapsing nor explosively inflating at present. Its expansion is gentle on cosmic timescales. The gravitational influence of vacuum energy, whatever its origin, is extremely small. This discrepancy is not subtle. It is not a matter of factors of 2 or 10. It spans many orders of magnitude. Quantum field theory predicts vacuum energy densities vastly larger than what is compatible with cosmological observations. The mismatch is so large that it cannot be attributed to experimental uncertainty or minor theoretical corrections. This creates the first clear sign of a deep conflict between quantum field theory and gravity. Each theory is extraordinarily successful in its own domain. Quantum field theory explains particle physics with unmatched precision. General relativity explains gravity, space-time, and cosmology with remarkable accuracy. But when vacuum energy is involved, the two theories refuse to cooperate. The source of the conflict is not mathematical inconsistency within either theory, it is conceptual incompatibility between their assumptions. Quantum field theory treats space-time as a fixed background on which fields fluctuate. General relativity treats space-time itself as a dynamical object that responds to energy. Vacuum energy sits precisely at the intersection of these viewpoints. In non-gravitational physics, vacuum energy can be shifted arbitrarily. Only energy differences matter. In gravity, absolute energy matters. There is no freedom to redefine the zero of energy globally without physical consequences. What quantum field theory discards as unobservable, general relativity insists on interpreting geometrically. This difference in attitude toward energy is not superficial. It reflects a deeper incompatibility in how the two theories define physical reality. One allows energy offsets to be ignored, the other does not. Once this is recognized, it becomes clear that vacuum energy is not a minor technical issue. It is a diagnostic. It exposes the limits of applying existing theories beyond their natural domains. The problem is not that vacuum energy is predicted, it is that its gravitational role is unclear. Attempts to simply cancel vacuum energy by hand fail for the same reason. Any cancellation mechanism must itself gravitate. Removing vacuum energy from the stress-energy tensor without a physical justification breaks the link between energy and geometry that defines general relativity. Suppressing its gravitational effect without suppressing its quantum effects requires a mechanism that no known theory provides. This tension was recognized long before observational evidence of cosmic acceleration. Theoretical physicists understood that vacuum energy and gravity were in conflict as soon as quantum field theory and general relativity were compared seriously. The observational discovery of accelerated expansion later transformed this conceptual problem into an empirical one. Vacuum energy should affect expansion because it fills space uniformly and contributes negative pressure. That is not an optional interpretation. It follows directly from the form of the stress-energy tensor. The real question is not whether vacuum energy affects expansion, but why its effect is so small. At this stage, no accepted theory provides a satisfactory answer. Some approaches attempt to modify gravity, others attempt to introduce new symmetries or cancellation mechanisms, others treat vacuum energy as an emergent or non-fundamental quantity. None of these ideas has achieved empirical confirmation. What is clear is that the conflict cannot be resolved within quantum electrodynamics alone, nor within classical general relativity alone. Vacuum energy forces the two frameworks into direct confrontation. It reveals that their coexistence is provisional. The vacuum, once again, proves to be a diagnostic tool rather than a passive concept. It is not just empty space with quantum decorations. It is the place where the deepest assumptions of modern physics collide. Energy must gravitate. The stress-energy tensor demands it. Vacuum energy is energy. Therefore, vacuum energy must gravitate. The fact that this reasoning leads to a contradiction with observation is not a mistake in logic. It is a sign that our current description of nature is incomplete. The first hints of that incompleteness appear precisely here, where the quiet background of empty space becomes a source of gravitational tension. The cosmological constant problem arises when vacuum energy, treated consistently in both quantum field theory and general relativity, is compared with what the universe actually does. Each framework is internally successful. Together, they produce a prediction that fails by an unprecedented margin. The problem is not subtle, technical, or aesthetic. It is numerical, physical, and extreme. In general relativity, a constant energy density filling space enters the equations of motion as a cosmological constant. This term determines how space-time expands when averaged over large scales. Observations of the universe allow this term to be measured. Independent cosmological probes, such as the expansion history inferred from distant supernovae, the structure of large-scale galaxy clustering, and the imprint of early universe fluctuations, converge on the same conclusion. The vacuum energy density driving cosmic expansion is small but non-zero. Quantitatively, the observed vacuum energy density is extraordinarily tiny when expressed in natural units. It corresponds to an energy scale far below those associated with particle physics. Despite its smallness, it has a clear gravitational effect. It causes the expansion of the universe to accelerate slowly over billions of years. This behavior is consistent across multiple observational datasets and is now a well-established feature of modern cosmology. Quantum field theory, however, gives a radically different answer. When the zero-point energies of quantum fields are summed, even conservatively, the predicted vacuum energy density is enormous. The precise value depends on how high in energy the theory is trusted, but the result is always vastly larger than what is observed. If the sum is cut off at energy scales associated with known particle physics, the predicted vacuum energy already exceeds the observed value by many orders of magnitude. If the sum is extended to scales where gravity is expected to become important, the discrepancy becomes extreme. The theoretical prediction overshoots observation by roughly 120 orders of magnitude. This number is not a rhetorical exaggeration. It is a direct comparison between two quantities expressed in the same units. No other known disagreement between theory and observation in physics comes remotely close. Typical discrepancies that motivate new theories involve factors of a few, perhaps a few hundred. A mismatch of 120 orders of magnitude is without precedent. This is why the cosmological constant problem is often described as the worst prediction in physics. It is not merely wrong, it is catastrophically wrong. If quantum field theory's naive prediction were even approximately correct gravitationally, the universe would not resemble anything we observe. Its expansion rate would be so large that structure could not form. Galaxies would never condense. Atoms might not exist. The fact that any structure exists at all already demands an explanation. The severity of the problem does not depend on speculative assumptions. It arises even when only well-established physics is used. Known quantum fields contribute to vacuum energy. Known principles of gravity demand that energy gravitate. Observations show that the resulting gravitational effect is tiny. The contradiction is direct. One might hope that some cancellation mechanism resolves the issue. Perhaps different contributions to vacuum energy cancel almost perfectly, leaving a small residual. At first glance, this seems plausible. Quantum field theory includes many fields with different properties. Some contributions are positive, others negative. Why not imagine that they sum to nearly zero? The difficulty lies in the required precision. To reduce a quantity predicted to be enormous down to the observed value, cancellations must occur to extraordinary accuracy. Contributions that individually differ by more than 100 orders of magnitude must cancel almost exactly, leaving a remainder that is fine-tuned to an extreme degree. Such cancellations are unstable. In quantum field theory, vacuum energy receives contributions from all energy scales. Changing the physics at high energies alters the vacuum energy at low energies. Unless protected by a symmetry, any delicate cancellation is destroyed by small changes in underlying parameters. No known symmetry enforces vacuum energy to vanish or remain small once quantum effects are included. Symmetries that protect particle masses or interaction strengths do not protect vacuum energy. Even if a cancellation occurs at one level of calculation, higher-order corrections reintroduce large contributions. Maintaining a small vacuum energy requires repeated, precise cancellations at every order. This sensitivity makes simple cancellation explanations physically implausible. They replace one mystery with another. Why should unrelated contributions cancel with such extreme accuracy? Invoking coincidence does not solve the problem, it restates it. Another tempting idea is to set the vacuum energy to zero by definition. In non-gravitational quantum field theory, the zero of energy can be chosen arbitrarily. However, gravity removes this freedom. The absolute value of energy matters because it curves space-time. Redefining zero energy does not eliminate gravitational effects, it only shifts labels. Attempts to modify gravity so that it does not respond to vacuum energy face similar obstacles. Gravity couples to the stress-energy tensor as a whole. Vacuum energy has the same tensor structure as a cosmological constant. Suppressing its gravitational effect without suppressing other well-tested gravitational phenomena requires highly specific modifications that risk contradicting observations. Some proposals suggest that vacuum energy is somehow sequestered or screened. Others invoke new degrees of freedom that adjust dynamically to cancel vacuum contributions. These ideas are mathematically sophisticated, but none has yet provided a compelling, experimentally supported resolution. What makes the cosmological constant problem particularly severe is that it sits at the intersection of otherwise successful theories. One cannot dismiss quantum field theory, nor can one abandon general relativity lightly. Both have been tested extensively and confirmed in their respective domains. The problem arises precisely because both theories are taken seriously. The mismatch also resists interpretation as a failure of approximation. It does not depend on unknown coefficients or uncertain parameters. It emerges from the structure of the theories themselves. The same calculations that successfully predict laboratory phenomena also predict vacuum energy contributions that are gravitationally unacceptable. This places the problem in a unique category. It is not an anomaly confined to a specific experiment or regime. It is a global inconsistency in how physical theories assign meaning to empty space. The problem also persists regardless of whether vacuum energy is interpreted as zero-point energy, potential energy of fields, or something else. Any constant energy density contributes gravitationally in the same way. Changing the interpretation does not change the gravitational effect. The observed value of the cosmological constant is not zero. This fact eliminates one potential escape route. If vacuum energy vanished exactly, one might hope for a symmetry enforcing that result. Instead, the universe exhibits a small but non-zero vacuum energy. Any explanation must account not only for why the value is tiny, but why it is not exactly zero. This smallness is itself puzzling. From the perspective of quantum field theory, there is no preferred scale for vacuum energy. All contributions are large. The observed value appears unnatural within the theory. It is far smaller than any scale that arises naturally from known physics. This notion of naturalness underlies much of the discomfort. In physics, parameters that are vastly smaller than expected usually signal hidden structure or new principles. The cosmological constant problem suggests that our understanding of vacuum energy is incomplete at a fundamental level. Despite decades of effort, no solution has achieved broad acceptance. Many ideas exist, ranging from modifications of gravity to new symmetries to multiverse scenarios. Each comes with its own conceptual costs. None has been confirmed experimentally. The persistence of the problem is itself informative. It suggests that vacuum energy is not a minor detail to be fixed within existing frameworks. It may be pointing toward a deeper reorganization of physical theory, one in which the relationship between quantum fields, spacetime, and energy is fundamentally rethought. The cosmological constant problem is therefore not just about a number. It is about the meaning of vacuum energy and the scope of our theories. It exposes a profound mismatch between how quantum field theory and gravity treat the most basic state of the universe. That mismatch remains unresolved. It stands as one of the clearest indications that modern physics, despite its successes, does not yet fully understand empty space. The concept of dark energy entered physics through observation, not theory. It was not introduced to fix an equation or rescue a model. It emerged because the universe was found to be behaving in a way that contradicted long-standing expectations. Instead of slowing down under the pull of gravity, cosmic expansion is accelerating. For most of the 20th century, cosmology assumed that the expansion of the universe should be decelerating. Matter attracts matter. Gravity pulls structures together. Even in an expanding universe, this attraction should gradually slow the rate at which galaxies move apart. The only open question was how strong the deceleration was, and whether it would eventually halt expansion altogether. That expectation was overturned in the late 1990s by measurements of distant supernovae. Certain types of stellar explosions act as reliable distance indicators because their intrinsic brightness can be inferred from their light curves. By comparing how bright these explosions appear to how fast their host galaxies are receding, astronomers can reconstruct the expansion history of the universe. The result was unexpected. Distant supernovae appeared dimmer than they should have been in a decelerating universe. The only consistent interpretation was that the expansion rate has been increasing over time. The universe was expanding more slowly in the past than it is now. Something is counteracting gravity on large scales. This conclusion was not based on a single observation or dataset. Independent teams using different samples reached the same result. Over time, the evidence only strengthened. The discovery forced cosmology to confront the possibility that a new component dominates the energy budget of the universe. Further support came from large-scale structure. The distribution of galaxies across cosmic distances carries a memory of how structures grew over time. In a universe dominated by matter alone, gravitational clustering proceeds in a predictable way. Observations show that structure growth has slowed relative to what would be expected if matter were the only driver. This slowing is consistent with an accelerating expansion stretching space faster than gravity can pull matter together. Measurements of the cosmic microwave background provide another line of evidence. Tiny temperature fluctuations imprinted when the universe was young encode information about its overall geometry and energy content. These measurements indicate that the universe is very close to spatially flat. Achieving flatness requires a total energy density near a critical value. The observed matter content falls far short of that value. The missing component behaves like a smoothly distributed energy density with repulsive gravitational effects. Together, these observations form a consistent picture. Roughly 2/3 of the total energy density of the universe appears to be in a form that does not cluster like matter, does not dilute rapidly with expansion, and drives accelerated expansion. This component is called dark energy. The name reflects ignorance, not understanding. Dark energy is not known to be a substance, a field, or a force in the traditional sense. It is defined operationally by its gravitational behavior. It contributes to the stress-energy tensor in a way that causes expansion to accelerate. Vacuum energy is a natural candidate for dark energy because it already has the required properties. A constant vacuum energy density fills space uniformly. It does not clump. It exerts negative pressure equal in magnitude to its energy density. In general relativity, this combination produces accelerated expansion. From a mathematical standpoint, vacuum energy and a cosmological constant are equivalent. Both correspond to a constant term in the equations governing space-time dynamics. Both act uniformly throughout space and time. Both produce the same large-scale gravitational effect. This equivalence makes vacuum energy an attractive explanation. No new fields or exotic dynamics are required. The effect is already present in the equations of general relativity. The observational signatures match the simplest possible model. A constant energy density that remains unchanged as the universe expands. The smoothness of dark energy is a crucial feature. Unlike matter, which clusters into galaxies and clusters under gravity, dark energy appears to remain evenly distributed. Observations show no evidence of dark energy concentrating around structures or forming localized clumps. Its influence becomes noticeable only on the largest scales, where the cumulative effect of uniform expansion dominates. This smoothness follows naturally if dark energy is vacuum energy. The vacuum state is defined by symmetry. It looks the same everywhere. There is no mechanism for it to pile up in one region rather than another. Any attempt to localize vacuum energy would break the symmetries that define it. This behavior distinguishes dark energy sharply from dark matter. Dark matter interacts gravitationally, but clusters like ordinary matter. Dark energy does not. It affects geometry rather than structure directly. The timing of cosmic acceleration is also notable. Dark energy did not dominate the universe from the beginning. In the early universe, radiation and matter densities were much higher. As the universe expanded, matter diluted while vacuum energy remained constant. Eventually, the vacuum component became dominant. This transition occurred relatively recently on cosmic timescales. This timing raises additional questions, but it does not undermine the observational case. The data consistently indicate that the expansion history matches a universe in which a smooth, constant energy density became dominant only after billions of years of matter-dominated evolution. From an observational standpoint, the simplest model fits remarkably well. When dark energy is treated as a cosmological constant, the predictions align with supernova data, large-scale structure measurements, and cosmic microwave background observations simultaneously. More complex models are possible, but none is required by the data. This success is also what sharpens the theoretical tension. If dark energy is vacuum energy, its observed value is extraordinarily small compared to what quantum field theory predicts. The universe behaves as if vacuum energy exists, but only barely. The acceleration is slow, gentle, and only noticeable over vast distances and long times. Dark energy therefore sits in an uncomfortable position. Observationally, it behaves exactly as a small vacuum energy would. Theoretically, there is no clear reason why vacuum energy should be so small. The smooth background behavior of dark energy is not an assumption added to fit the data, it is an inference drawn from multiple independent observations. Any explanation must reproduce this uniformity and persistence over cosmic time. Whether dark energy truly is vacuum energy or something more subtle remains open. What is clear is that cosmic acceleration is real, well measured, and incompatible with a universe containing only matter and radiation. The discovery of accelerated expansion transformed vacuum energy from a theoretical curiosity into an empirical necessity. The vacuum is no longer just a background state discussed in particle physics. It appears to shape the fate of the universe itself. In this way, dark energy links the smallest scales of quantum theory with the largest scales of cosmology. It turns the question of what empty space contains into a question about how the universe evolves. Vacuum phase transitions arise when the lowest energy state of a quantum field changes as physical conditions evolve. In modern cosmology, this idea is not an optional embellishment. It follows directly from combining quantum field theory with an expanding, cooling universe. As the universe evolves, the properties of its vacuum can change, and when they do, the consequences are global. At extremely high energies, such as those present in the early universe, symmetries that are hidden today can be exact. Fields that now have non-zero background values may once have been centered at zero. Interactions that now distinguish between different particle species may once have treated them identically. In this regime, the vacuum is defined differently. It reflects the symmetries available at those energies. As the universe expands, it cools. Cooling does not merely reduce particle motion, it changes which vacuum states are energetically favoured. When a symmetry that was stable at high temperature becomes unstable at lower temperature, the vacuum can undergo a phase transition. This is analogous to familiar transitions such as the freezing of water, but the underlying mechanism involves quantum fields rather than atoms. In a quantum field, symmetry breaking occurs when the shape of the field's potential energy changes. At high energy, the lowest point of the potential may lie at a symmetric configuration. As conditions change, that point can become unstable, and new minima appear elsewhere. The field then settles into one of these new configurations. The vacuum is redefined. This process is called spontaneous symmetry breaking. The laws governing the field remain symmetric, but the vacuum state does not. Once the vacuum chooses a particular configuration, the symmetry is no longer manifest in the behavior of particles. Masses, interaction strengths, and force ranges can all change as a result. In cosmology, such transitions are unavoidable. The early universe passed through a wide range of energy scales. At each stage, different vacuum configurations could have been favoured. Each transition reshaped the physical environment in which particles evolved. A crucial distinction in this context is between a true vacuum and a false vacuum. The true vacuum is the configuration of a field with the lowest possible energy. A false vacuum is a configuration that is locally stable but not globally minimal. A system in a false vacuum can remain there for long periods, even though a lower energy state exists elsewhere. This situation arises naturally in quantum field theory. The potential energy of a field can have multiple minima separated by energy barriers. If the field sits in a higher energy minimum, it is trapped unless it acquires enough energy to cross the barrier or tunnels through it quantum mechanically. In the early universe, false vacua are not exotic. They are expected. High temperatures and rapid expansion can trap fields in metastable configurations. These configurations define the vacuum state at that time, even though they are not the lowest energy state available in principle. The distinction matters because false vacua behave gravitationally. A false vacuum has higher energy density than the true vacuum. That energy contributes to space-time curvature. While the field remains trapped, the universe responds to that energy density as if it were a cosmological constant. This idea plays a central role in inflationary cosmology. Inflation posits a period of extremely rapid expansion in the early universe. During this phase, the universe was dominated by vacuum-like energy associated with a scalar field in a metastable state. This vacuum state was not the true vacuum of the field, but it was stable enough to persist for a finite time. While the field remained in this state, its energy density stayed nearly constant. As the universe expanded, matter and radiation diluted, but the vacuum energy did not. The result was accelerated expansion at an extraordinary rate. Space itself expanded faster than any signal could travel through it. This inflationary vacuum was not permanent. Eventually, the field transitioned to a lower energy state. When this happened, the energy stored in the false vacuum was released into particles and radiation. This process reheated the universe and set the stage for the standard hot Big Bang evolution. In this framework, vacuum properties determine the large-scale structure of the universe. The duration of inflation, the rate of expansion, and the spectrum of primordial fluctuations all depend on the shape of the vacuum potential. Tiny quantum fluctuations of the field during inflation were stretched to cosmic scales, seeding the density variations that later grew into galaxies. Vacuum phase transitions can also leave relics. Depending on how a transition proceeds, it may produce topological defects such as cosmic strings or domain walls. These structures arise when different regions of space choose different vacuum configurations that cannot be smoothly reconciled. While no such relics have been definitively observed, their possible existence constrains models of early universe physics. The key point is that vacuum is not a static backdrop. It is a dynamical entity whose properties depend on energy scale and environment. As the universe cooled, the vacuum changed. Each change altered the rules governing particles and forces. Importantly, these transitions do not require new physics beyond quantum fields and gravity. They are generic features of field theories with multiple vacuum states. Once such fields exist, vacuum evolution becomes inevitable in a cosmological setting. False vacuum states also illustrate why vacuum energy cannot be dismissed as irrelevant. Even if a vacuum state is temporary, its gravitational influence can dominate cosmic evolution while it lasts. Inflation demonstrates this explicitly. A vacuum state lasting a fraction of a second reshaped the entire observable universe. This realization reframes the vacuum as an active participant in cosmic history. The universe did not merely evolve within a fixed vacuum. The vacuum itself evolved, and its evolution drove major transitions. Vacuum decay is governed by quantum mechanics. A false vacuum can persist for long periods because transitions require tunneling through energy barriers. The probability of decay depends on the shape of the potential and the height of the barrier. Some false vacua are extremely long-lived, persisting far longer than the age of the universe. This introduces the possibility that the present vacuum may itself be metastable. Whether this is the case depends on details of fundamental fields that are still being investigated. The possibility alone highlights the physical meaning of vacuum states. They are not arbitrary reference points. They are dynamical configurations with consequences. What matters for cosmology is not whether a vacuum is true or false in an absolute sense, but how it behaves gravitationally and how long it persists. A vacuum with higher energy density drives faster expansion. A transition to a lower energy vacuum releases energy and changes expansion dynamics. In this way, vacuum properties shape cosmic history directly. They determine expansion rates, influence structure formation, and control the thermal history of the universe. The vacuum is not merely the absence of particles between events, it is a central actor in the universe's evolution. This perspective also clarifies why vacuum energy cannot be treated as a trivial offset. During phase transitions, differences in vacuum energy drive dramatic physical effects. If vacuum energy were physically meaningless, inflation would have no mechanism. Vacuum phase transitions therefore serve as concrete evidence that vacuum energy is real, dynamical, and gravitationally relevant. They demonstrate that changing the vacuum changes the universe. From the earliest moments of cosmic expansion to the present epoch of dark energy dominance, vacuum states have shaped the trajectory of space-time. The universe we observe is the result of a sequence of vacuum configurations, each defining a different set of physical conditions. In this sense, cosmic history can be read as the history of the vacuum itself. The Higgs field provides the most concrete and experimentally verified example of how vacuum structure determines the properties of particles. It shows in a direct and measurable way that the vacuum is not merely a passive background, but an active physical state whose configuration fixes fundamental features of the universe. In the case of the Higgs field, those features include the masses of elementary particles themselves. In quantum field theory, every field has a vacuum state, the configuration of the field with the lowest possible energy. For many fields, this lowest energy configuration corresponds to a field value of 0. The Higgs field is different. Its lowest energy state corresponds to a non-zero field value everywhere in space. This non-zero value is called the Higgs vacuum expectation value. The phrase vacuum expectation value has a precise meaning. It does not mean that the Higgs field fluctuates wildly around 0 and occasionally takes on a value. It means that when the field is in its ground state, its average value is not 0. The vacuum itself carries a constant Higgs field permeating all of space. This single fact transforms the nature of empty space. Even in the absence of particles, even at absolute 0, the Higgs field does not vanish. Empty space contains isonant Higgs background with a fixed magnitude. That background is as real as the electromagnetic vacuum, but its effects are far more dramatic. Mass in this framework is not an intrinsic property carried by particles independently of their environment. It is an interaction with the vacuum. Elementary particles acquire mass through their coupling to the Higgs field. The stronger the coupling, the more massive the particle appears. This mechanism resolves a deep theoretical problem. Without the Higgs field, the equations governing particle interactions would forbid mass for many particles. Gauge symmetries that ensure consistency and predictability require particles to be massless at a fundamental level. Introducing mass by hand would break those symmetries and render the theory inconsistent. The Higgs field solves this by allowing symmetries to remain intact at the level of the equations while being hidden by the vacuum state. The laws remain symmetric. The vacuum does not. This is spontaneous symmetry, breaking in its most familiar and experimentally confirmed form. When the Higgs field settled into its non-zero vacuum state in the early universe, particles interacting with it began to behave as if they had mass. This was not a sudden creation of mass as a substance. It was a change in how particles propagate through space. Their equations of motion were altered by the ever-present Higgs background. Different particles interact with the Higgs field in different ways. Some couple strongly and become heavy, others couple weakly and remain light. Some, such as photons, do not couple at all and remain massless. These differences are not imposed arbitrarily. They reflect how each field interacts with the Higgs vacuum. This explains why particles with otherwise similar properties can have vastly different masses. It also explains why mass is universal and stable. As long as the Higgs vacuum remains unchanged, particle masses remain fixed everywhere in the universe. The Higgs field therefore makes mass a property of the vacuum, not of particles in isolation. Remove the Higgs vacuum, and the concept of particle mass as we know it disappears. Space itself would behave differently. Forces would have different ranges. Atoms could not form. This reframes empty space in a striking way. The vacuum is not just filled with fluctuating fields. It is filled with fields whose non-zero background values determine the basic structure of matter. The vacuum does not merely influence interactions. It defines what particles are allowed to be. The stability of this vacuum configuration is therefore not a minor detail. If the Higgs vacuum were unstable, the masses of particles could change, or the vacuum could transition to a different state with radically different physical laws. The Higgs potential, the function that determines which field values are energetically favored, allows for the possibility of multiple vacuum states. The vacuum we inhabit corresponds to one of these states. Whether it is the absolute lowest energy state or merely a metastable one is a question of intense theoretical interest. Current measurements suggest that the present Higgs vacuum may be metastable rather than absolutely stable. This means it could, in principle, decay to a lower energy state. Such a decay would involve a transition of the Higgs field to a different vacuum configuration, changing the values of fundamental constants and particle masses. However, metastability does not imply imminent danger. The lifetime of such a vacuum, if metastable, appears to be enormously longer than the age of the universe. The probability of decay within any relevant timescale is vanishingly small. For all practical purposes, the vacuum is stable. What matters physically is not whether the vacuum is absolutely stable, but whether it persists long enough to define a consistent universe. The current Higgs vacuum does exactly that. It has defined particle masses and interactions for billions of years. The possibility of metastability, nevertheless, reinforces an important point. Vacuum states are physical configurations with real consequences. They are not abstract reference choices. They can change, and if they do, the universe changes with them. The Higgs field also illustrates how vacuum structure can differ between fields. Not all fields acquire non-zero vacuum values. Not all vacuum structures are associated with symmetry breaking. The vacuum is not a single uniform concept. It is a collection of field configurations, each governed by its own dynamics. This complexity is essential for understanding why particles interact with the vacuum differently. Each field couples to the Higgs field with its own strength. Those couplings are parameters of the theory, determined by experiment. The vacuum provides the background, but the response depends on the field. This also explains why the Higgs vacuum does not produce forces in the usual sense. Unlike the electromagnetic field, the Higgs field's vacuum value is uniform. There are no gradients to produce forces. Its influence appears only through the modification of particle properties. In this sense, the Higgs field demonstrates a new role for the vacuum. It is not merely a source of fluctuations or energy. It is a medium that endows particles with identity. Mass is not something particles carry with them independently of space. It is something they acquire from space itself. This insight generalizes beyond the Higgs field. Other vacuum fields can, in principle, shape physical laws in similar ways. The Higgs field is simply the one case where this effect has been observed directly. The discovery of the Higgs field confirmed that vacuum structure is experimentally accessible. It is not confined to speculative cosmology or abstract quantum corrections. It operates at energy scales probed in laboratories. It determines measurable quantities. This also deepens the vacuum energy problem. The Higgs vacuum carries energy. Its non-zero value contributes to vacuum energy. yet its gravitational effect appears to be either extremely small or cancelled by other contributions. The same vacuum that gives particles mass seems not to curve space-time catastrophically. This coexistence of profound vacuum effects at the particle level with negligible gravitational impact at cosmic scales sharpens the conceptual tension. It suggests that vacuum structure and vacuum energy are not simply related in a straightforward way. The Higgs field therefore occupies a central position in the story of the vacuum. It shows that the vacuum can be structured, non-zero, and physically decisive without destabilizing the universe. It also shows that our understanding of how vacuum properties translate into gravity remains incomplete. Empty space, as revealed by the Higgs field, is not empty at all. It is filled with a field whose presence gives mass to matter and defines the architecture of the physical world. The vacuum is not the absence of something, it is the condition that makes something possible. In this way, the Higgs field turns the vacuum from a passive concept into a foundational one. The universe is not built on top of empty space, it is built out of the vacuum itself. Vacuum metastability follows directly from the idea that the vacuum is a physical configuration of fields rather than a mere reference level. If a field's potential energy has more than one minimum, then more than one vacuum state exists. The universe occupies one of them. Whether that state is the absolute lowest energy configuration or only a local minimum determines whether the vacuum is stable or metastable. A metastable vacuum is not unstable in the everyday sense. It does not decay spontaneously or fluctuate violently. It is stable against small disturbances. The field can remain in this state indefinitely unless a rare quantum process allows it to transition to a lower energy configuration. In practical terms, metastability means longevity, not fragility. Vacuum decay refers to such a transition. Physically, it would mean that a field currently defining the vacuum configuration tunnels through an energy barrier and settles into a different minimum of its potential. The vacuum state itself changes. Because the vacuum defines particle properties, forces, and energy densities, such a transition would alter the basic laws governing physics in the affected region. This is not a rearrangement of matter within space. It is a change in what space itself supports. The vacuum after decay would not be a modified version of the old one. It would be governed by different field values, different particle masses, and potentially different interaction strengths. The concept of vacuum decay therefore refers to a change in the ground state of the universe, not to an explosion or disruption in the classical sense. Quantum field theory provides a precise mechanism for how such a transition could occur. Even if a field is classically trapped in a local minimum, quantum mechanics allows tunneling through energy barriers. This is the same principle that allows particles to cross classically forbidden regions. Applied to fields, tunneling does not occur at a single point but over a finite region of space. The result is bubble nucleation. A small region of space undergoes a transition to the lower energy vacuum. This region forms a bubble whose interior is in the new vacuum state, while the exterior remains in the old one. If the bubble is large enough, it becomes energetically favourable for it to grow. The boundary between the two vacua expands outward at a speed approaching that of light. Inside the bubble, the laws of physics are determined by the new vacuum. Outside, they remain unchanged until the boundary arrives. There is no warning signal propagating ahead of the boundary. The change is abrupt, at the moment the boundary passes. This description often leads to dramatic imagery, but it is important to remain precise. The process is governed by field dynamics and quantum probabilities. It is not an explosion that sends debris outward. It is a reconfiguration of the vacuum state itself. The rate at which such bubbles nucleate depends sensitively on the shape of the field's potential. The height and width of the energy barrier separating vacua determine how likely tunneling is. For most reasonable potentials, the tunneling probability is extraordinarily small. This is why metastable vacua can persist for immense periods. Even if a lower energy vacuum exists, the probability of nucleating a bubble within any given region of spacetime can be so tiny that the expected lifetime of the metastable vacuum exceeds the age of the universe by many orders of magnitude. In the case of the current vacuum state, theoretical analyses suggest that if it is metastable, its lifetime is vastly longer than the present cosmic age. This conclusion is robust across a wide range of assumptions. Small changes in parameters do not make the decay rapid. The vacuum, if metastable, is deeply metastable. This extreme longevity explains why vacuum decay is not considered an imminent concern. It is a theoretical possibility, not a practical hazard. The universe has existed for billions of years without undergoing such a transition, and there is no evidence that the probability is increasing. Cosmic expansion further suppresses decay. As space expands, regions of space become causally disconnected. Even if a bubble were to nucleate somewhere, it would affect only the region within its future light cone. The vastness of the universe does not make decay more likely in any locally meaningful sense. Vacuum decay is also constrained by observational consistency. The laws of physics appear uniform across the observable universe. There is no evidence of regions with different vacuum properties. This uniformity places strong limits on any decay processes that might have occurred in the past. The apparent stability of the universe is therefore not mysterious. It is the natural consequence of field potentials that allow long-lived metastable states. Stability does not require absolute minimal energy. It requires barriers that are sufficiently robust against quantum tunneling. This distinction is essential. In everyday language, stability is often equated with being at the lowest possible energy. In quantum field theory, stability is a dynamical concept. A system can be stable for all practical purposes even if a lower energy state exists, provided transitions are sufficiently suppressed. The possibility of vacuum decay nevertheless has conceptual importance. It reinforces the idea that the vacuum is not a fixed, immutable background. It is a physical state governed by dynamical laws. Its persistence is not guaranteed by definition, but by the structure of field potentials. It also highlights the difference between local physics and global considerations. The vacuum state defines local particle properties and interactions. Its decay would redefine those properties. That such a redefinition is even conceivable underscores how deeply the vacuum is woven into the fabric of physical law. Importantly, vacuum decay does not require external triggers. It is not caused by collisions, cosmic rays, or experiments. It is an intrinsic quantum process. No known physical activity can catalyze it in a meaningful way. This further reinforces why it is extraordinarily unlikely within any relevant timescale. The universe appears stable because, according to current understanding, it occupies a vacuum configuration protected by substantial energy barriers. Whether this vacuum is absolutely stable or merely metastable does not alter the observable fact that it persists. From a theoretical standpoint, metastability is not a defect. It is a natural outcome of quantum field dynamics. Many systems exhibit long-lived metastable states. The vacuum is no exception. The lesson is not that the universe is precarious, but that stability is a physical property that emerges from dynamics rather than definitions. The vacuum is stable because the laws governing fields make it so. In this way, metastability and vacuum decay deepen the picture of empty space. They show that the vacuum has structure, alternatives, and a history. They also show that the universe we observe is not an arbitrary state, but one selected by both dynamics and extreme longevity. The quiet persistence of the vacuum is therefore not trivial. It is the result of quantum mechanics operating on the largest possible scale. Vacuum energy becomes most problematic precisely where the usual division of labour in physics breaks down. In ordinary quantum field theory, fields fluctuate on a fixed space-time background. In ordinary general relativity, space-time curves in response to energy and momentum, but space-time itself is not quantized. Vacuum energy forces these frameworks to interact in a regime where neither set of assumptions is fully consistent. In flat space-time quantum field theory, vacuum fluctuations are defined relative to a stable notion of time and energy. That stability allows modes to be labelled, particles to be defined, and a unique ground state to be identified. In curved or time-dependent spacetime, these concepts become observer-dependent. What one observer calls vacuum, another may describe as a state filled with particles. Even the distinction between positive and negative energy becomes ambiguous. As a result, the notion of a single, universal vacuum state breaks down. This immediately complicates any attempt to calculate vacuum energy. The familiar procedure of summing zero-point energies over field modes relies on assumptions that no longer hold globally. In curved spacetime, such sums are not invariant under changes of coordinates or observers. Meaningful calculations require careful renormalization that focuses on local, finite quantities rather than absolute energies defined everywhere. What survives are differences, responses, and expectation values, not a straightforward number that can be inserted into gravity without qualification. The deeper issue is conceptual rather than technical. Standard quantum field theory treats space-time as a passive arena. Vacuum energy, however, is a uniform energy density. In general relativity, a uniform energy density curves space-time globally. If the vacuum energy is large, the resulting curvature would be large as well. That curvature would invalidate the assumption of a fixed background on which the vacuum energy was calculated in the first place. The calculation undermines its own foundations. This self-referential problem signals that ordinary perturbative methods are being pushed beyond their domain of validity. The vacuum energy is being computed as though space-time were rigid, even though its gravitational effect would make space-time highly dynamical. This is not a minor inconsistency. It strikes at the heart of how quantum theory and gravity are combined. The difficulty becomes sharper when renormalization is considered. In quantum electrodynamics, infinities arise but can be absorbed into a finite number of physical parameters. The theory remains predictive because only a small set of quantities needs to be fixed by experiment. Gravity behaves differently. When treated as a quantum field theory in the same way, its coupling strength causes higher energy contributions to generate ever more severe divergences. Each order of calculation introduces new types of terms involving space-time curvature. This means that gravity, in this formulation, is not renormalizable in the same sense as QED. An infinite number of parameters would be required to absorb all divergences. Predictive power is lost if the theory is pushed to arbitrarily high energies. This does not mean gravity cannot be treated quantum mechanically at all. It means that the straightforward perturbative approach does not yield a complete fundamental theory. Instead, gravity is best understood as an effective field theory at low energies. In this framework, quantum corrections can be calculated systematically as long as energies remain far below the scale where quantum gravity becomes dominant. For many purposes, this approach works extremely well, but vacuum energy is not a small correction. It is a constant offset that influences space-time on the largest scales. It does not decouple cleanly from high-energy physics. As a result, the effective field theory perspective does not tame the vacuum energy problem. Once gravity is taken seriously as a dynamical field, another layer of complexity appears. If spacetime geometry is subject to quantum principles, then spacetime itself must fluctuate. Distances, durations, and causal structure acquire quantum uncertainty. At everyday scales, these fluctuations are negligible. Near the Planck scale, they become dominant. Vacuum fluctuations of matter fields already generate stress-energy fluctuations. In a quantum theory of gravity, those fluctuations would feed back into space-time geometry. Curved geometry, in turn, alters the definition of vacuum and the spectrum of fluctuations. The vacuum ceases to be a state defined on a single classical spacetime and becomes something associated with an ensemble or superposition of geometries. This feedback loop has no analogue in non-gravitational quantum theory. It highlights why vacuum energy is such a sensitive probe of quantum gravity. It is precisely the quantity that links microscopic quantum fluctuations to macroscopic space-time behavior. Because a full quantum theory of gravity is not yet available, physicists often adopt a semi-classical approximation. In this approach, matter fields are treated quantum mechanically, while space-time remains classical. The curvature of space-time is determined by the expectation value of the quantum stress energy tensor. This framework is internally consistent in many regimes and makes real predictions. Semi-classical gravity predicts effects such as particle production in curved space-time. A vacuum defined at one time may not remain a vacuum at another, leading to observable radiation even in the absence of classical sources. It also predicts vacuum polarization effects, where quantum fields subtly modify the effective behavior of gravity. However, semi-classical gravity does not resolve the vacuum energy problem. The expectation value of the vacuum stress energy still behaves like a cosmological constant. Renormalization can remove local divergences, but it does not explain why the remaining value is so small. The theory faithfully transmits the problem rather than eliminating it. Some of the most suggestive clues about this impasse come from horizons. Event horizons around black holes and the cosmological horizon in an accelerating universe possess thermodynamic properties. They have temperatures and entropies proportional to their surface areas. These are precise results, not analogies. The existence of horizon thermodynamics implies a deep connection between space-time geometry, quantum theory, and information. A cosmological constant creates a horizon. If vacuum energy behaves like such a constant, then it is directly tied to horizon entropy and temperature. This links vacuum energy to global information-theoretic properties of space-time rather than to a simple sum of local field modes. This perspective suggests that the naive calculation of vacuum energy may be counting degrees of freedom in a way that gravity does not respond to directly. Gravity may be sensitive to information encoded on horizons or to collective properties of space-time rather than to raw zero-point energies summed over volume. While this idea remains incomplete, it offers a hint that the mismatch may lie in how vacuum degrees of freedom are organized, not merely in their magnitude. What emerges from all of this is a consistent pattern. Quantum field theory makes vacuum fluctuations unavoidable. General relativity makes energy gravitational. Standard methods work when these ideas are applied separately, but vacuum energy forces them into direct confrontation. Semi-classical gravity shows that the confrontation is physically meaningful and predictive, while also revealing that it cannot be resolved within existing frameworks. The vacuum, in the presence of gravity, is no longer just a property of fields. It becomes a property of space-time itself. That shift marks the boundary of current understanding. The difficulty is not that the calculations are sloppy or incomplete. It is that the concepts they rely on reach their limits. Vacuum energy in quantum gravity therefore acts as a signpost. It indicates where our most successful theories cease to be sufficient, and where a deeper description of space-time and quantum fields must eventually take over. Vacuum energy forces modern physics to confront the boundaries of its own success. The difficulty does not arise because existing theories are weak or poorly tested. It arises because they work extremely well within their intended domains, yet give incompatible answers when applied to the most basic state of reality. The vacuum is where those domains overlap most sharply, and where their assumptions can no longer be kept separate. Quantum field theory treats the vacuum as the ground state of fields defined on spacetime. General relativity treats space-time as a dynamical object shaped by energy and momentum. Both frameworks are internally coherent. Both are empirically successful. Vacuum energy sits precisely at the junction where they must be applied simultaneously. The resulting tension is not technical, it is structural. This is why vacuum energy exposes the limits of current theory so clearly. In non-gravitational physics, vacuum energy can be shifted, subtracted, or ignored without consequence. In gravity, no such freedom exists. Energy has geometric meaning. The fact that the same quantity can be dismissed in one framework and is compulsory in the other reveals that at least one set of assumptions must eventually be revised. The vacuum therefore acts as a stress test for fundamental ideas. It tests whether space-time can truly be treated as a fixed background. It tests whether energy can be defined independently of geometry. It tests whether local field degrees of freedom are the right variables for describing gravitational phenomena. The failure of these assumptions to coexist peacefully is not a flaw in calculation, it is a diagnostic signal. One lesson is that the vacuum is not merely the absence of particles, it is a physical state whose properties depend on deep principles. Its energy, symmetry structure, and fluctuations are determined by how fields are defined, how symmetries are broken, and how quantum uncertainty is implemented. If gravity responds to those properties in unexpected ways, the issue cannot be resolved by adjusting parameters. It requires rethinking how the vacuum itself is defined. This makes the vacuum a probe of deeper laws. It is not something added to theories after the fact. It is the baseline configuration from which all excitations are measured. Any theory that claims to be fundamental must specify what its vacuum is and why that vacuum behaves as it does. If two theories disagree violently about the vacuum, they cannot both be complete. Historically, progress in physics has often come from taking such disagreements seriously. The incompatibility between classical mechanics and electromagnetism led to special relativity. The incompatibility between classical physics and atomic stability led to quantum mechanics. Vacuum energy presents a similar incompatibility, but at a deeper level, because it involves space-time itself. The vacuum also connects disparate areas of physics that otherwise seem unrelated. It links particle masses to symmetry breaking. It links cosmic expansion to quantum fluctuations. It links horizon thermodynamics to information theory. It links ultraviolet physics to infrared behavior. Few concepts span so many scales simultaneously. This breadth is precisely why empty space may hold the key to unification. A unified theory must explain not only particles and forces, but why the vacuum they inhabit has the properties it does. It must explain why vacuum energy gravitates weakly, why vacuum fluctuations affect local physics but not catastrophically distort space-time, and why the vacuum appears uniform across cosmic distances. Attempts at unification that ignore the vacuum tend to reintroduce the problem in another form. Any new field, symmetry, or interaction comes with its own vacuum structure. Unless the theory explains how vacuum contributions combine and gravitate, the cosmological constant problem simply reappears at a different level. This suggests that the vacuum is not a passive byproduct of unification, but a central constraint on it. Whatever deeper laws govern nature must make the vacuum behave in a way consistent with both quantum phenomena and gravitational observations. That requirement is extraordinarily restrictive. At the same time, the vacuum resists oversimplification. It cannot be reduced to a single number or parameter. It includes zero-point fluctuations, background field values, symmetry-breaking configurations, and possibly space-time degrees of freedom themselves. Treating all of this as a single energy density is an approximation whose limitations are now evident. One possibility is that vacuum energy is not a fundamental observable in the way quantum field theory suggests. It may be emergent, relational, or defined only in specific contexts. Gravity may respond not to raw vacuum energy, but to some coarse-grained or constrained aspect of it. Horizon thermodynamics hints in this direction, suggesting that information and geometry are intertwined in ways not captured by local field theory. Another possibility is that spacetime itself is not fundamental. If spacetime emerges from more basic degrees of freedom, then vacuum energy calculated within a spacetime-based framework may not correspond directly to what gravity responds to. In such a picture, the enormous vacuum energy predicted by field theory could be an artifact of applying space-time concepts beyond their domain of validity. What matters is not which idea eventually succeeds, but what the vacuum tells us now. It tells us that local quantum fields on a smooth space-time background are an approximation. It tells us that energy, geometry, and information cannot be treated independently at the deepest level. It tells us that empty space is not empty of structure, and not simple enough to be dismissed. At the same time, the vacuum does not license speculation without constraint. Any proposed resolution must reproduce the extraordinary successes of existing theories. It must explain why quantum field theory works so well for particles and forces. It must explain why general relativity works so well for gravity and cosmology. And it must explain why the vacuum sits quietly between them, influencing both without destabilizing either. This is why restraint is essential. The problem of vacuum energy does not invite dramatic conclusions about imminent vacuum decay, exotic universes, or hidden dimensions without evidence. It invites careful attention to what current theories actually say, where they agree and where they fail. The open questions are therefore precise, even if the answers are unknown. Why does vacuum energy gravitate so weakly? Why does the vacuum select the particular symmetry-breaking patterns we observe? Why is the vacuum stable on cosmic timescales? Why does the vacuum appear uniform across regions that were once causally disconnected? Why do quantum fluctuations shape structure without overwhelming space-time curvature? None of these questions can be dismissed as philosophical. They arise directly from applying well-tested theories consistently. Their persistence indicates that something essential is missing from the current framework. What vacuum energy ultimately tells us is not that physics is broken, but that it is incomplete. The vacuum is not a nuisance term to be regulated away. It is the quiet background against which all physical processes unfold, and its behavior encodes information about the deepest level of description. Empty space, when examined carefully, refuses to be empty. It carries energy, structure, symmetry, and history. It shapes particles and space-time alike. If a unified description of nature exists, it will not bypass the vacuum. It will explain it. Until then, vacuum energy remains both a success and a challenge. A success because its effects are real and measurable. A challenge because its meaning is not yet fully understood. That combination makes it one of the most reliable guides to where the next fundamental insight must come from.